What is up? Florida Man Does Weather. We are back with why is snow forecasting so hard? It's something you hear about all the time from regular people. They're always going to be griping about how the meteorologists completely fumbled a snow forecast where it's like, oh, you said I'd get 1 to 3 inches, we got 10. Or you said I'd get 10 inches of snow and we got two. It's very, very difficult, people. So when you're forecasting something like this on screen, that's hard. Go to that next image. And if you're forecasting this is freezing rain, all ice accretion, all sleet. This is also hard. Why is it so hard? Let's go to our sounding types. So you've got snow, sleet type sounding, and a freezing rain type sounding in the left. From left to right.
Mhm.
So with snow, you've got freezing temperatures all through the column, sufficient moisture for snow growth within that little snow growth region. This sounding, your snow growth is kind of happening anywhere above 800 millibars to about, I would say, 550. Once you get up above there, you have a little bit less moisture and you're not getting ice crystals forming. But that type of sounding profile supports a snowflake forming and surviving that fall thousands and thousands of feet to the ground. Even though it's, marginal close to freezing temperatures, it's still going to support that snow reaching the ground. And then you have in the middle, you have sleet. So you've got snowflakes that have formed and then they hit that above freezing mark and they start melting down. So since snow is a crystalline structure, it starts to melt from the little outer reaches first, and then it'll kind of just condense into this little core of ice, and it'll be like kind of wet. So then once it falls through that above freezing layer, you now have a water droplet, and then it goes
Mhm.
below that above freezing layer, and it's really cold once again. So then it refreezes as a little ball of ice. That's your sleep. And then for freezing rain, the most frustrating type. So you can have straight snow fall into that layer. It's now a completely melted water droplet. And then it falls specifically with this sounding. These wouldn't even really have much time to be your super cooled droplets. So these would freeze on contact, but your initial drops aren't going to freeze on like your trees. They're just going to cool everything down. And then once you have just that tiny bit of ice buildup on your tree limbs and everything, then you would get that big accretion layer forming. But this type of sounding, this is more like your roadways are going to be completely cooked immediately. But why is this so hard to forecast? Let's go over to our models. So this is what we see prior to the event. So this is a long ways out on the GFS. Just pulling this for example, this is sounding over Michigan. This is 100% going to change.
Yeah, absolutely.
So at this point, go scroll a little bit further down.
Okay.
At this point, your sounding does support snow. You have sufficient moisture in your snow growth region. Like this is just prior to a snow event, basically within the model itself. This is right before it starts to kick off snow in Michigan on this run. So you have just enough moisture to begin your snow growth. And notice you're below freezing all the way down. That little blue line that goes up and to the right from the 0 degree mark, that's your freezing line in your atmospheric sounding.
Right
So
here.
everything it's to the left of that. Everything is still below freezing. You would have snowflakes falling and making it to the ground, other than that little dry air layer just above the 850 millibar mark, that would do something we call evaporative cooling and moistening. So your snowflakes basically just evaporate there, and it helps to cool and moisten your profile a little bit further. Isn't that wet bulbing? That's what that is.
Yeah, and so if anybody out there, if you have gone on a hike before, I'm big on hiking in cold weather, particularly mountain hiking and stuff up in the Smokies and the Alleghenies whenever it's cold. Uh, Whenever a snow flurry or a snow shower starts while you're hiking on a mountain, if you've been on a mountain, you notice before the snow even starts happening, you will get a sudden gust of wind, and it won't be necessarily a strong gust of wind, but you will get a rush of wind, and it will be significantly colder and significantly more humid than the ambient air mass that you have been in. That's what Caleb's referring to with the evaporative cooling. As those snowflakes evaporate, because the air around them is dry, it creates a pocket of humid, cold air. As that continues to sink, that's paving the way for the snowflakes to fall in behind it. So that's why when you're hiking, or I mean, and not even you don't even have to be hiking. You could be anywhere else. I'm just using hiking as an example because I'm big on that. You'll notice that rush of cold, moist air right before the snow event starts. Is because those first flakes sacrificed themselves to prime the environment, so the ones behind them ended up surviving and making it all the way to the surface.
Hmm. And then X out of this sounding and take it to
Oops.
no. Like
Yeah.
yeah, still on that actual model. But let's take it to the freezing rain uh precip area. So with this kind of a little low setup, I think it was hour 186,
Yeah, it was.
and then click right in that pink region right there. So with this kind of a low setup, you're going to have a warm advection regime. And this is the resolution you're working with in a model. So it's depicting a warm nose precip event where you're going to have that warm air trying to push north, fighting against that cold air. So you're going to have at some level, usually in your lower levels, usually around 850 millibars is where this will happen. You'll have your frontogenesis band where your warm front kind of like slants its way up, and you're going to have this overrunning warm air over your cold air. And on this model, it's way less pronounced right there than it usually would appear. So this
Yes.
is depicting freezing rain where you basically have super cooled droplets. It's just warm enough to melt your snowflake into a water droplet, but not
About
quite
one
cold enough to
Celsius right
freeze
here.
them.
It
Yeah.
hits about 1 Celsius right here. So just a quick note. So if you look over here in the corner, it says dendritic growth zone, -12 to -17 C. That's going to be your snow growth region on this. So if you look right here, okay, these isotherms that run on a slant, your -12 zone to -17, that would be right here. So if you follow that on a diagonal, it's going to be from right about here. So right about, I would say, what would that be, Caleb? About 650 millibars?
Yeah,
Yeah.
probably.
I think it's this mark right here, the 13,160. So about 13,160 feet, all the way up to about
Oh yeah, perfect.
15,561. That's going to be your snow growth region. Then, like Caleb said, the air warms as you get into that warm nose as you get closer to 0 degrees. And for a little bit, right about day 50, it gets on the model. And obviously, this is very simplified because it's a model that's running way, way, way out. Um, we're just using this as an example. It hits 1 degree Celsius at 850, which is just enough to start melting some of those flakes and turning them into water. And then it kind of rides right above that freezing zone. So it's sitting like right there. It's not warming up enough to the point that it fully converts into a raindrop state. It's kind of just right in that line. And then it dips back down to 30 Fahrenheit right when it hits the surface. So you've got a ton of water droplets sitting right between going back and forth between 30 and 32 degrees Fahrenheit. And then the surface there is obviously well below freezing. So when it hits the ground, you're obviously going to get that first bit of accumulation as a liquid, like Caleb was saying. And once that freezes on the surface, it's not going to take much energy to take the rest of your 32 Fahrenheit water. When it hits the surface, they'll convert it to ice. So there, the ice just immediately starts forming as the second wave, if you will, of moisture hits the ground.
And all of this, the whole idea behind this video really came about from my own personal forecast that I completely got blown on. And yeah, it was for Randolph, New Jersey. It's a spot where I've lived. I know the tendencies around there pretty well. And all of the models were forecasting, good snow, really good snow for the northern New Jersey and New York City and like the Connecticut area. all of that was supposed to be really, really good snow. I personally forecast 5 to 10 inches. The National Weather Service for Philadelphia, Mount Holly, they forecast, I think, around 6 to 8. And they ended up adjusting midway through the day for a 4 to 6 inch snowstorm. And I'm watching the precip reports come in on radar scope, and it's all sleet, freezing rain, snow, sleet, freezing rain, snow. I check their radar. I'm looking for your mixed layers, and it's right over Morris County where Randolph is. And that's when I knew I'm cooked. This snow forecast is going to be way, way off. So how much snow did Randolph end up getting? About 3.4 inches. So the National Weather Service and me, we both ended up getting wrong on our snow amounts. And even the southwest corner of Morris County, I can't remember the town name, but I saw an ice accretion report of 0.49 inches come in from them. They were only forecast to get maybe a tenth of an inch of ice accretion from freezing rain. So that is a huge difference. And the reason why is because one, there are no soundings launched in New Jersey. They're all from Upton, New York. That's really your closest spot that can be representative of your New Jersey atmosphere. And even Upton, New York, which is like on Long Island, they were still within a snow profile when the Zero Z sounding launched on, I can't remember the date, but it was the most recent snowstorm up there. So they had a snow profile, but you could see these little warm layers were starting to be picked up on their sounding as snow was falling. They were just still below freezing, so they all still supported snow, but it was there. So for New Jersey, which is just right over there, especially with Morris County, that's a very close proximity in terms of distance between the Upton, New York sounding and Randolph, New Jersey. For them to get such a massive discrepancy in snowfall and precip type, the warm layers over Morris County had to be pretty well pronounced because this snow event was a very cold snow event. I believe it was about 26 to 24 degrees for most of this. And if you're getting freezing rain at 24 degrees, that is a stout warm layer above the surface for that to melt down and then end up freezing at the surface. And then here's the other part of snow forecasting that's hard. X out of this sounding and go to one that is north of Michigan in the dry air. So oftentimes forecasting the northern extent of your snowfall with especially honestly I think it's harder on weaker low pressure systems as well. So yeah, go with the UP. That should do it. So why wouldn't it snow here? It's sufficiently cold enough. You've got all types of cold air. You've got just enough forcing. But what do you have? You have very, very dry air. So just below your snow growth region is a very stout layer of dry air. So those snowflakes are going to fall and they're just going to fizzle out. They're going to evaporate. You might get snow flurries with that kind of environment, but you're not going to get accumulating snow. And even this says best guess precip type is rain. I think that's just the model being a little bit inaccurate because at 33 degrees with no real warm layers above freezing in that sounding, you'll see snowflakes. They'll survive to the ground, but they're not going to
They're gonna
amount to
melt.
anything.
They're gonna melt on
Yeah,
contact. So what
yeah,
would end up happening is your dry slot would end up mixing out a little bit as the snowflakes fell through it, but it would not be significant enough to when you say warm nose, you say it in context here because everything is still below that zero
mhm.
isotherm. So your warm nose, the dry layer there would kind of mix out, but your ground layers are still at 33 Fahrenheit. And that's one of the things that makes snow prediction so complicated. Caleb, me and you were just talking about this the other day. The difference between 33 Fahrenheit and 32 Fahrenheit, or even 33 and 31, if that surface temperature of 33 were to drop, say, 1 or 2 degrees more to 31, you will start having snow accumulate on the ground. It's literally snow forecasting is so tricky because you have phase changes in water right there. So, I mean, it just takes 1 degree of difference to change everything. And that's what makes snow predictions so complicated and so frustrating.
Yeah. Like of all the forecasting types you can do, I would say snow forecasting is definitely your hardest. Fire
Absolutely.
weather is probably up there because the growth and spread rate is that gets a little complicated when you're talking about all your dry air and your winds and when's the wind going to kick up in terms of how dry it's going to be and all that. And then probably a couple of your easiest, honestly, severe weather, in my opinion, that's the easiest one
Oh
just
yeah.
because I'm the most used to it. But snow, we don't have to deal with that in Florida. That's why we've been challenging ourselves to forecast snow events this year because we want to be good at everything. We want to be the best as we possibly can at everything.
Yeah.
But next time a meteorologist gets your snow forecast wrong, have a little bit of sympathy. It's hard. All right. Thank you guys for watching the video. We'll be back with some more forecasting pretty soon, actually.